Hey everyone, thank you for tuning in. I hope you're all having a great virtual conference. My name is Serena, and I'm a data scientist on the multi-channel data team at Shopify in Toronto. One of the most common questions I get from friends who are familiar with machine learning but don't work in data science is how do you decide what data to use to train a model? So today I'm going to talk a little bit about that process, which we call feature engineering. By the end of this talk, I hope that you'll be familiar with the concept of feature and what that means in terms of data science, and understand what feature engineering is and why it's important. And we'll also go over some basic techniques and practical examples of feature engineering. Before we jump into that, I want to take a step back and define our problem space. Data science is a relatively young discipline, and there's an ongoing discussion on its definition and how it relates to various fields. But in the day-to-day practice of organizations, a data scientist is someone that works to manipulate data and extract meaning from it using tools from statistics, computer science, and some common sense and judgment too. So a data scientist is typically involved in a variety of activities, and some of them are strictly technical, like data collection, processing, and analysis. But some require more human intuition, like understanding the domain of the problem, identifying what information is going to be relevant to solve it, and making recommendations to the business on the basis of the results of the analysis. So a data scientist sits between engineering and business, bridging the gap between the two. Now, reality is messy, so representing it meaningfully with numbers is challenging, and it requires a fluid and iterative process. So typically, you'll start with a question or a problem to solve, and you want to get to some insights and a way to communicate them or action them. Um, but you'll go through this like fluid, nonlinear process, and you'll probably iterate through a few of the steps one time, a few times, maybe all of them over and over before you're set on an approach. Um, so feature engineering sits at the center of this process. And in general, you'll have to iterate on it at least once or twice before coming up with an approach that will work for your problem. So what is a feature? In software design, it's an intentional distinguishing characteristic of a piece of software. And so that might refer to functionality or performance, but that's not what we mean in machine learning. In machine learning, a feature is an individual measurable property or the characteristic of an object of analysis. And so it's equivalent to the concept of variable in statistics. And in fact, I'm going to use variable and feature with the same meaning in this talk going forward. Um, so if you're thinking of a data set, your columns, those are your variables and those are your features. Feature engineering is the process of manipulating raw data to produce features that represent the problem at hand. Um, Doing so by extracting information, highlighting patterns, and incorporating domain knowledge. So it lets us feed our analytical tools meaningful input, and it's the best way to improve machine learning models. More data beats clever algorithms, but better data means more data. I really like this talk. I feel like it really summarizes a lot of what data science is. It's another question that I get often is how much data do I need? How much data do I need to solve this problem? How much data do I need to train this model and have it answer correctly? The answer generally is more, but really what you need is more quality data. The concept of garbage in, garbage out is all but new in tech, but it really becomes super relevant in the context of data science. So because the implications can be quite serious. So first of all, machine learning models are not smart per se. No matter how fancy your math is, simple algorithms can outperform more complex ones if they're trained on enough quality data. And the other side of the coin is that incorrect, inconsistent, and biased data leads to wrong conclusions. So the implications can be quite serious, especially as companies rely more and more on data and models to make decisions. Now let's make an example to really understand what feature engineering means. Let's say we have a bunch of photos And we want to train a model to be able to recognize if the object in the photo is a motorcycle. In machine learning, this is called a classification problem. And so for each photo, we want the algorithm to assign one of two labels, motorbike or non-motorbike in this case. The problem of feature engineering then translates to finding a set of inputs, or features, which describe the photo in a way that makes it easier for the model to assign the label correctly. Let's take a few seconds to internalize where the problem comes from. So, as humans, we see a combination of shapes and colors, but the machine sees an array of numbers, and each of these numbers will be representing a color, um, the color of a pixel in the photo. So, we need to find a way to represent it or to feed it to the model. Let's assume that we want to just use the raw data and that we want to limit the complexity of our model. So, instead of passing the entire array of pixels, we just pick two. Um, the naive approach would be to take two pixels on the photo and feed them to the model. And this is equivalent to asking, for example, given that one pixel is gray and one pixel is blue, is there a motorbike in this photo? So that's a pretty hard question to answer, even for a person. And so if we use this set of raw features, any learning algorithm will struggle to accurately classify our images. An alternative approach might be to create new features. So we'll create two binary features. Wheels is true when the object in the photo has wheels and false otherwise. And handlebar, very similarly, is true when a handlebar appears in the photo. Now, the question that we're asking to the algorithm this time is, given that there are wheels and handlebar in this photo, is this a motorbike? And so this is much easier to answer. The model will not always be right, but training it on this set of features will yield much more accurate results. Both examples only use two features, but the second set of features performs better because it embeds information that is more relevant to discriminating between two classes. Intuitively, knowing that there's some pixels are gray and some pixels are blue it's way less meaningful than knowing that there are wheels and a handlebar in the photo. So hopefully you're starting to see how we can obtain wildly different results with the same number of inputs, with the same number of features. Um, that concept of better data, not necessarily more data. And so using domain knowledge, motorbikes have wheels and they have handlebars. Using this knowledge, we were able to create new features that represent the problem space efficiently and increase the accuracy of our model. This is a quote that I love. Coming up with features is difficult, time consuming, and required experts' knowledge. Applied machine learning is basically feature engineering. Now, feature engineering is rarely formalized in theory, and sometimes different data science will have slightly different opinions on what counts as part of the process and whatnot. For example, some might include some data cleaning steps under feature engineering, and some may not. But the bottom line is that there are many ways to tackle any problem, and no single way to create features to a given use case. So, how do you come up with features? The optimal set of features depends on the domain of the problem, the questions we're trying to answer, the data that is available. So the best approach really is talking to experts, practice, poke around your data, experiment, try different things, iterate on it. For the next part of the talk, I will go over an example um, and show how you would go about creating some features and training a model on a data set. Um, I'm going to use the Kickstarter dataset. It's publicly available on Kaggle. And so Kickstarter is a crowdfunding platform. And this is a collection of a little over 300,000 projects that were set up on the website between 2009 and 2018. So in this dataset, each row represents one of these projects. And it contains information such as the name, when it was launched, what was the monetary goal, what was the state of the project at the time of the export, and so on. We have category and a few other things. Um, for the rest of the talk, I'll go over some examples of feature engineering techniques that are commonly used day to day and that can be applied to this example. I won't be showing any code just because it's not particularly inspiring, but feel free to reach out to me after the talk and I'll share a link to a notebook if you're interested in it. Step one, the very first thing we need to do is to define a problem. And so, in the context of feature engineering, this is really defining our target, prepare it for or to be passed to our model. In machine learning, the target is what in statistics we call predicted variable. So it's the outcome that we want to predict. And so it's super important that we define it well. The table on the left here shows a count of projects by state. And the first thing we're going to do here is removing the projects that were live at the time of the exports. We don't have ground truth about this. We don't know if they were successful or not. And so we just take them out of the analysis completely. So our task is to define a set of features that we can use to predict if a project is going to be reaching its crowdfunding goal or not. And so we actually transform the state column into a new feature, into a target feature, which is just success or not. The first thing we're going to look at is categorical features. These are features that can take on one of a limited set of possible values and assign each unit of observation to a particular group or a particular category based on some qualitative property. You see we have a few in our data set. Categorical features always need processing because learning algorithms can only process numerical values. Most algorithms use linear algebra or some other form of math. That doesn't go well with strings. It only takes numbers. And so we'll take a couple of features, a couple of raw features here and manipulate them so that we can use them into a model. But we won't look at all of them. The first and most common way to process categorical variables is one-hot encoding. What that means is that you take each category in your original variable and you create a binary feature for each of the categories in the original data. So if the first record main category was publishing, all of the new binaries will have value 0 for this project, except for the one related to publishing. And so project 2 and 3 are in the category film and video, and also have zeros all the way, except for film and video, the column related to film and video, and so on and so forth. This is a super common way to do it, and it yields this result, this matrix as a result. So we started with one raw feature, and now we have 15 or something like that. For the second example, we'll look at currency. And we have the counts of currencies here. So we could probably process it the same way with one-hot encoding. But if we look at the distribution of projects across currencies, we can see that the vast majority of goals are set in USD. So in the interest of reducing complexity and the number of inputs, we create a single binary feature and group all of the other currencies together. So it's going to become, is it this project's goal set in USD? This is really what we did for the target just before, but there's no need to use this technique again. There's no reason to not use this technique again, especially because it allows us to keep the number of features down and reduce the complexity of the model. So going back to that concept that better data, informative data, is better than more data. Dates and times, time steps are another data type that learning algorithms don't process as is. So there's typically a bit of work to be done in terms of processing temporal features. This can be as simple as extracting time features like the time of the day or the time of the month, or doing something more elaborated like working with time deltas or creating time series features, looking at the trends, looking at cycles, or anything else that you can think of. For these examples, I've made some simple assumptions. So this is where you're really kind of embedding the domain knowledge. And to be fair, I don't really have a lot of domain knowledge, but I'm making some assumptions here. One is the time of the day and the weekday may affect how visible the project is in first place. And so that might affect how many people decide to pledge money. And two, the time between launch and the deadline can probably have an influence on the results. So having more time might be more helpful, for example. So I mostly worked with the launched column and extracted the hour of the day and the week the project was launched. I created a numerical variable for the hour launched, and a binary variable for whether it was launched on a weekday or not. So whether it was launched between Monday and Friday or on the weekend. Um, and then I calculated the difference between the launch date and the deadline of the project. Next are numerical features. They are the easiest to manipulate. And like I said before, there isn't a standard sets of steps to take or a technique to apply. There's a couple of things to keep in mind. Most algorithms will require that you normalize numerical values before passing them as input. This is so that all numerical values have the same scale, but don't lose the difference between data points. For this example, I'm actually using a random forest classifier in terms of algorithm, which is robust to differences in scale. So we don't actually need to normalize the features before training, but this isn't the case for many algorithms. So keep that in mind if you're working with one. And then another point to remember is that most algorithms cannot handle missing data. So it's good practice to impute them before. Um, there's a whole field of statistics that we don't have the time to go into. But it's good practice to make sure that you don't have missing data. And if you do, fill them in with some sensible value. And you can count that as feature engineering as well. And then finally, you really can get creative with this and experiment with many transformations. So here I decided to create a new feature representing the number of projects launched in the same week, under the assumption that maybe having a lot of projects coming out at the same time makes it harder for someone to even discover a project that they want to pledge money to. Now we have engineered a few features, and we want to fit them to a learning algorithm to build a predictive model for success of the project. The features we have are related to category. We have one for each category that was originally in the main category column. Then we have ISUSD, which is a binary referring to the currency, whether the goal of the financial goal is expressed in USD or not. There's the hour the project was launched, whether it was launched on a weekday or not, the days to the deadline, and the 7 days count of projects launched in the same week. So I used a random forest classifier, which generally performs well with minimal parameter tuning, and optimization was a little bit beyond the scope of this example. So the accuracy of the model isn't great, it's around 60%. But again, we did absolutely no optimization. And this is actually just the first pass that we took at feature engineering. A nice thing about random forest, and one of the reasons why I used it, is that you can, it provides a normalized score for each feature importance. So you can see highlighted in green which features were had more predictive power. So the features related to music, technology, and theater in terms of categories. So but knowing whether the category is one of these three can be helpful or more helpful in predicting whether the project would be successful or not. And then the next two features that were more useful is the goal. So the amount of money that the person or the project is trying to fund, and the dates to the deadline. So the time between launch and when it's supposed to be wrap up. So typically we'd take this output and iterate onto the process. So use it to inform which features we might be dropping, the ones that maybe are less useful, and maybe iterate over this process a few more times. So we'll drop some, maybe add some more, experiment a little bit more with some of the features or the raw data, and then train and test again. And we do that basically until we're happy about the accuracy of the model. So once again, there is no golden rule to solve feature engineering, and there's no single unified approach that will guarantee the optimal set of features for a given use case. The features that you're going to extract and how you're going to combine them depends on the domain of the problem, the kind of insight you want to produce, and what data is available. So like many other things in data science, this is a fluid, iterative approach that involves a lot of trial and error. Often, you will return to revise your features as more data becomes available, as priority shifts, or as the insights that you originally produced with your model seem less accurate or less a little bit off reality. Talking to experts, practice, and experimentations are all excellent ways to understand the problem, develop intuition for what might work for a specific one. And so, typically, as you repeat this process over and over, as you work with more data, as you see more different data types, you develop intuition for, oh, this technique might be working well with this specific type of data or the specific problem. So it may look like magic, but it really is about having curiosity and sort of explore the elements that best describe and summarize a problem. And so developing intuition for how to represent them as numbers.